For covalent bonding, just as it says covalent, we will look at nonmetals sharing of electrons to build bonds. Previously, we had worked with metals and nonmetals, generating ionic compounds in which an electron is transferred from a metal to a nonmetal, positive ion and a negative ion held together with the plus-minus. Then we moved on for a short time to metals bonding with metals, since most metals are solid. Clearly there's something holding them together. We talked about the sea of loose valence electrons surrounding each nucleus and the inner core of electrons, and then the valence electrons surrounding. Alloys made of metals doing the same thing. And now at last, here we are looking at nonmetals bonding with nonmetals. Molecular bonding, also known as covalent bonding. We'll be drawing some Lewis structures invented by Gilbert Lewis way back in the day, and his Lewis dot structures will attempt to account for all of the valence electrons in an atom. Again, valence electrons, not total number of electrons. So 4 basic steps. We're going to sum the valence electrons. We're going to pay attention to whether or not we're drawing a Lewis structure of an ion, a polyatomic ion, at which point if it is a negative ion we will add in some extra electrons for negative ions, and we will subtract an electron or more if it is a positive polyatomic ion. So sum the valence electrons, connect all the atoms with single bonds, use electrons to complete an octet for all the atoms present, a duet of course only for hydrogen because it is so small. So we'll put electrons around each atomic symbol, and then if we find that we don't have enough electrons to go around, we will use multiple bonds, double bond, maybe a triple bond. But it's important that we only add in one multi-bond at a time. We don't want to end up with too many multiple bonds and end up with more than an octet for atoms. So we'll start with fluorine, and we can find fluorine on the periodic table with 7 valence electrons. 7 times 2, that's 14 electrons. Total is all that we can have in the molecule, but I'm going to draw a Lewis dot structure first, representing atomic symbol as if there were 4 sides representing the 4 valence orbitals, an S and a P, P, and P. And so we'll put 1, 2, 3, 4, 5, 6, 7 electrons around one of the fluorines, and I'll draw another fluorine and put 7 electrons around it. And then these atoms, when they come close enough and form a bond, that bond will hold these 2 atoms together and make a molecule. And what we want to make sure of is that each we've provided for 14 total electrons, which we certainly have, and that each atom has an octet. But very quickly it becomes tedious counting dots, and so we're going to change each pair of electrons into a line and draw a Lewis structure just using lines. And so if we were to redraw this, we would say fluorine first, bond with a single bond, and notice that 14 electrons of course means we can have 7 lines in our structure. So I've used up 1 line, 2, 3, 4, 5, 6, 7, representing F2. Next would be hydrogen. Hydrogen of course has only 1 valence electrons, 2 electrons total. Not a lot of option but to simply bond the hydrogen together. Let's move on to oxygen, which we can find in the periodic table here with 6 valence electrons. Again, not total electrons, but valence electrons. So we have 6 times 2, that's 12 electrons, which of course is 6 lines. So we'll put down an oxygen and bond it to the other oxygen, and we'll put in our unshared pair. And so I've used 1 line, 2, 3, 4, 5, 6 lines total, and you can see at this point that this oxygen on the right does not have an octet. The oxygen on the left does have an octet around it. So when we don't have enough electrons to go around, what we'll need to do is move an electron pair from one of the atoms that has enough into the middle. So I'm going to get my eraser out and move an electron pair in between and create what's known as a double bond. We would call these electrons that we are surrounding each atom with, we'd call them unshared or non-bonded pairs of electrons. And so you can see with the line structure that each oxygen has an octet, but we've done that still with only 12 electrons. We cannot end up with simply putting too many electrons in the structure. That would not be allowed, because that would be 14 electrons, not 12 valence electrons. Nitrogen on the periodic table, we can see here, has 5 valence electrons. 5 times 2, 10 electrons, 5 lines. Nitrogen bonded to another nitrogen. We've used up one line, 2, 3, 4, 5, and we can see that neither nitrogen, now you may have instead done something like this, but still the nitrogen on the left comes up short, and as a result we'll need to get the eraser out and put an electron pair in between and get the eraser again, perhaps remove this one and put the electron pair here. Now it absolutely does not matter where you place these unshared pairs. They could be here, it could be down at the bottom, it doesn't matter. All we need to see is that the nitrogen on the left has an octet, 4 lines, and the nitrogen on the right has an octet, 4 lines. Methane, CH4, is what comes out of our Bunsen burner. If we add our valence electrons, carbon has 4, plus 1 for each hydrogen times 4, that's a total of 8 electrons. Carbon in the middle, hydrogen singly bonded to each singly bonded to the carbon in the middle, and we end up with 4 bonds for the carbon and 1 bond for each hydrogen. So on to ammonia, nitrogen with its 5 valence electrons plus 1 times 3 for the hydrogen. That again is 8 electrons with the nitrogen in the middle, 3 hydrogens bonded to it. And so I've used up 3 lines. Of course I have a total of 4 lines, and the 4th line will end up as an unshared pair on the nitrogen. Again, the nitrogen has an octet, and the hydrogen each has 2 electrons. Next, water. 1 times 2 for the hydrogen plus 6, also 8 electrons. Each hydrogen bonded on either side of the oxygen, and they'll be, to make up the 4 lines, 2 unshared pairs. Again, it certainly would be fully acceptable if you had drawn your structure this way. Either one is fine. And then this last structure, difluoromethane. If we add the valence electrons, we have 4 for carbon, plus 1 times 2 for the hydrogen, plus 7 times 2 for a total of 20 electrons. We'll put the carbon in the middle, put a hydrogen on one side and down the other, and attach each fluorine. And of course I've only used 4 lines, so I'll come in with 5, 6, 7, 8, 9, 10. Now each fluorine has an octet, the carbon has an octet, and each hydrogen with its duet. It absolutely does not matter if you have drawn the carbon in the middle and the fluorines on opposite sides, either side to side or top and bottom. At this point in drawing Lewis structures, all we concern ourselves with is the arrangement and attachment of the atoms, and not actually spatially how they're arranged, but rather who's attached to who.